Hello everyone, this is the audio recording for visually impaired students from the textbook Modern Approach to Organic Chemistry, written by Dr. J.M. Sehgal. Today, we will read about Chapter 3, Epoxides. So let's start. Article 3.1, Introduction. Epoxides are classic ethers having three-membered rings in which oxygen is one of the atoms. They are also known as alkene oxides or oxiranes. The simplest epoxide is ethylene oxide. Other examples of epoxides are epoxide or oxirane, ethylene oxide. In the common system, epoxides are called as ethylene oxides. In the IUPAC system, they are named as alkene oxides, epoxyalkenes or oxiranes. The common and IUPAC name of some epoxides are given below for the sake of illustration: ethylene oxide, propylene oxide, butene oxide, cyclohexene oxide. The chemical behavior of epoxide is quite different from acyclic ether. Synthesis of epoxide. First, epoxidation of alkenes. Epoxides are usually prepared by reaction between an alkene and an organic peroxide. The reaction is known as epoxidation. RCH double bond CHR plus R dash C double bond OH in the presence of epoxidation gives RCHO CHR plus R dash C double bond OH. Peroxides commonly used in this reaction are peroxyphoric acid HC double bond OOH, peroxyacetic acid, peroxybenzoic acid, and M-chloroperoxybenzoic acid. When a solution of peroxide acid and alkene in ether or chloroform is allowed to stand, epoxide is formed. For example, 2-butene plus peroxybenzoic acid gives 2,3-dimethyl oxide. Second, cyclohexane plus peroxybenzoic acid gives cyclohexene oxide. Third, 1,2-dimethylhexene plus C6H5C double bond OOH gives C6H5CH3OCH3 plus C6H5C double bond OOH. It may be noted that epoxidation of alkenes is a stereospecific reaction in which the stereochemistry of the substituents on the double bond is maintained. Thus, a cis-alkene gives a cis-epoxide and the trans-alkenes give a trans-epoxide. The reagent most commonly employed for exportation of alkenes these days is magnesium monoperoxythylate MMPP. Mechanism. The mechanism of the epoxidation involves the transfer of an electrophilic oxygen atom from peroxic acid to alkenes as depicted below. Second, from halohydrines. When halohydrines prepared by reaction of aqueous solution of chlorine or bromine with alkenes are treated with the base, HX is eliminated to yield an epoxide. For example, CH2 double bond CH2 plus Cl2 plus H2O gives HOCH2 CH2Cl plus HCl. This is known as ethylene chlorohydrin. Second example is HOCH2 single bond CH2Cl plus KOH gives CH2O CH2 plus KCl plus H2O. This is known as ethylene oxide. Mechanism. The base attacks the halohydrine to abstract the hydrogen from OH part of halohydrine to form an alloxide ion. The nucleophilic oxygen of the alloxide ion displaces the halogen from the adjacent carbon to form the epoxide as shown below. It may be seen that the reaction involves intramolecular, that is, within the same molecule, nucleophilic substitution and is therefore treated as intramolecular Williamson synthesis. It should also be noted that, as in SN2 reactions, the attack of nucleophile takes place from the backside of CX bond. Third, manufacture of ethylene oxide. Ethylene oxide is manufactured by passing a mixture of ethylene and air under pressure over silver catalyst at 475 to 675 Kelvin. 2CH2 double bond CH2 plus O2 gives 2CH2O CH2. Article 3.3 Chemical reactions of epoxides. In contrast to acyclic ethers, which are chemically quite inert, epoxides show high chemical reactivity. This is due to the highly strained nature of the three-membered ring system. Ring operating reaction of epoxides. In the three-membered rings containing oxygen, the COC bond angle and the CCO bond angle are nearly 60 degrees each. This large distortion from the normal tetrahedral angle of 109.5 degree causes very large strain in the epoxide molecule. As a result, epoxide undergo a number of ring opening reactions quite easily. These reactions take place through the cleavage of one of the carbon-oxygen bond and may be either catalyzed by acids or brought about by bases or nucleophiles. Article 3.3.1 Acid catalyst ring opening. Just as simple ethers undergo cleavage of the molecule on reaction with acids, epoxide undergo ring cleavage on treatment with acids even under mild conditions. First, acid catalyst hydrolysis. One of the most important cleavage reaction of epoxide is their hydrolysis to form 1,2-glycols. Hydrolysis takes place even in the presence of dilute mineral acids at room temperature. Epoxide plus water in the presence of H positive gives glycol. For example, ethylene oxide plus water in the presence of H positive give ethane 1,2-diol. Second, acid catalyst reaction with alcohols. For example, CH2O CH2 plus CH3CH2OH in the presence of H2SO4 gives CH3CH2O CH2CH2OH, means 2-ethoxyethanol. Third, reaction with halogen acids. Epoxide reacts with HCl and HBr to form chloroacid bromohydrins. For example, CH2O CH2 plus HBr gives CH2Br single bond CH2OH, means ethylene bromohydrin. Mechanism of acid catalyst ring opening. The mechanism of acid catalyst ring cleavage may be illustrated by considering the hydrolysis of epoxide. In the acid catalyst hydrolysis of epoxide, the epoxide is initially protonated by the acid. Article 3.3.2 Nucleophilic ring opening. Unlike simples, ethers which do not undergo ring cleavage by a base or a nucleophile, cleavage of epoxide ring take place even by such reagents due to the ring strain in their molecules. For example, when treated with OH negative ions at high temperature, epoxide's ring get cleaved to form 1,2-glycols. CH2O CH2 means ethylene plus H2O in the presence of OH negative gives CH2OH single bond CH2OH, means ethane 1,2-diol. Mechanism of nucleophilic ring opening. The mechanism of nucleophilic ring opening is shown below with the help of basis hydrolysis of ethylene epoxide. Article 3.3.3 Orientation of ring openings. First, anti-addition. The ring opening of epoxide leads to the formation of products corresponding to anti-addition to carbon-carbon double bond. For example, acid catalyst hydrolysis of cyclopentylene oxide yields trans 1,2-cyclopentane-diol. For example, cyclopentane oxide plus water gives trans 1,2-cyclopentane-diol. Second, Regioselectivity. Unsymmetrical oxyranes can undergo ring opening in two different ways and generally lead to different products in acidic and basic media. In acidic medium, the nucleophilic generally get attached to the more substituted carbon, while in basic medium, the nucleophilic becomes attached to less substituted carbon. Isobutylene oxide plus CH3OH gives CH3C, CH3O, CH3 double bond CH2OH. Explanation. The difference in regioselectivity in acidic and basic medium may be justified as follows. In basic medium, the ring opening is an SN2 displacement by the nucleophile on the unprotonated oxyrane. As in another SN2 reactions, the attack takes place at the less substituted and less trilically hindered carbon. In acidic medium, the first step is the protonation of the oxygen of the oxyrane ring. Due to the electron releasing group attached to more substituted carbon, positively charged oxygen attached to electron pair of its bond with this carbon to a greater extent than the electron pair of bond with the less substituted carbon. As a result, the more substituted carbon-oxygen bond becomes weaker than the less substituted carbon-oxygen bond. Therefore, ring opening takes place preferably at the more substituted carbon-oxygen bond and the product contains the nucleophile attached to more substituted carbon. In Article 3.3.4, other nucleophilic ring opening reactions. First, reaction with Grignard reagent and organolithium reagents. Epoxides also undergo nucleophilic ring opening reactions with Grignard reagent and organolithium reagent. The product initially formed on hydrolysis yields a primary alcohol containing large number of carbon atoms. The epoxide generally used in this reaction is ethylene oxide and the alcohol formed contains 2 carbon atoms more than in the Grignard reagent. For example, N-propyl magnesium bromide plus CH2O CH2 in the presence of ether gives 1-pentanol. N-butyl lithium in the presence of ether gives 1-hexanol. Second, reaction with alcohols. CH2O CH2 plus CH3OH in the presence of CH3ONA gives 2-methyl oxide 1-ethanol. Third, reaction with ammonia. CH2O CH2 plus NH3 gives 2-amino 1-ethanol. Fourth, reaction with hydrogen cyanide. CH2O CH2 plus HCN in the presence of water gives ethylene cyanohydrine. Fifth, reduction with LiAlH4. 4CH2O CH2 plus LiAlH4 gives CH2 single bond CH2O single bond AlLi in the presence of 2H2O gives 4CH3CH2OH plus LiAlO2. Thank you.